let's talk about those twinkling stars now. So come on, sing it with me now. I know you're sitting there just watching the video, and I'm sitting here by myself with a microphone, but let's do it together. Come on. 3, 2, 1. Twinkle, twinkle, little star. That's as far as I go. Sorry about that. I only sing in the shower. Okay, let's talk about the twinkling stars, though. So, here's the Earth. And you might be this little person standing here on the Earth, just sort of looking up at the sky and wondering about all those little white dots and all that sort of thing up there. And it turns out that if you look very carefully at stars, and hopefully you can do this maybe next time you're outside, is look at them very carefully. They're definitely twinkling. And by twinkling, I mean they're sort of fluttering on and off with their light. And let's just see why they might do that. So here's a star right here. And let's say we're trying to look at this star. So the way we'd see the stars, of course, is this light just streams an incredible distance across the whole galaxy. In some cases to go into our eye and we get to see it. So sort of like a privilege, right? The light has been traveling for a very long time all the way across into our eye so we can see it. But don't forget, what the light encounters as it approaches us on Earth is our atmosphere. So remember, there's this atmosphere that we sort of live in, that the light has to penetrate through before it gets to us. Okay, and it's down here too. There's the atmosphere for us. Okay. Now you got to think. What happens to light when it goes from the vacuum of outer space, which might have an n of 1.000, into the atmosphere here, which I don't know what it has, might have an index refraction of 1.0007. Remember, the air is a little bit different than the vacuum of outer space. There's an n1 and there's an n2 right there. So 1.000, 1.007, something like that. What happens? Well, we know that when it hits this point, it's going to refract. Right? Light always bends when it enters these interfaces. Well, so what about that? Well, it looks like it's going straight down and what could possibly refract, but you have to remember something about the atmosphere itself here. Let me maybe zoom in on a part of the atmosphere right here. You have to remember that the atmosphere is not a very constant sort of uniform entity. Okay, and by what that I mean is, let me get a little blue out here and go, well, sometimes there might be a lot of wind or pressure differences that might sort of maybe for a few seconds make the atmosphere, oh, that's way too thick, might make the atmosphere really thick right here for a second. But then what might happen is the air continues to blow, maybe a half a second later or something like that. The thickness might sort of just go away. It's like I got rid of my whole atmosphere, didn't I? The thickness might just sort of go away, right? But then the air might keep going and the thickness might come back. So it might get thick again. Then the thickness might go away as the wind blows, or it might even get thicker or something like that. It might get really thick. But the point is that with all this thickness is the, I guess my moral here is the, I can't draw when it's that thick, is the atmosphere. Let me get a decent color going here too. Too thick, sorry about that. Darn technology. Okay, let's say the atmosphere's N is always changing. In other words, as wind and clouds and moisture and humidity and pressure all move in the atmosphere right here, there might be some moments where the index refraction of the air is 1.0007. Then like a bunch of wind might come in and it might become a 1.0008, or it might drop to 1.006, or go up to well, I don't think it'll get that high, but it might go up to 1.01 or something like that. It's always changing. And this is just say, let's just chalk it up to our dynamic atmosphere. And we're talking about wind and clouds and fog and just anything you can think of that might be in our atmosphere might be moving in the way of this light beam, okay? And when that happens, you have to think about your law of refraction now, okay? So let's draw maybe in this red point right here, this red point right here. Let's draw a little interaction point. Let's say that's the boundary between outer space and the atmosphere as far as my light ray is concerned. Well, what'll happen is if the light ray encounters maybe a very thick atmosphere at that moment, it might sort of bend this way a tad bit, or it might bend that way a tad bit, or it might go straight down into your eye. Okay, but let's just think about that for a minute. If the light ray from the star comes in and bends this way, it's not going to go into your eye. And so the star is going to get a little bit dimmer. It's going to flutter a little bit. Or if it goes down this way, it's not going to go into your eye. It's going to flutter a little bit. Or it might go straight through into your eye, in which case you will see it, so it'll suddenly brighten again. So the issue with the stars twinkling are that is sort of this picture right here, is this interaction right here, is the twinkling has to do with, let's just say, shifting light rays due to atmospheric disturbance. And we can qualify that disturbance pretty well, not just any disturbance. We're talking about changing N of the atmosphere. That's what the disturbance is, right? The N is changing, and it's sort of steering the beam around. So shifting or steering of light rays due to atmospheric disturbance. Again, sometimes the starlight goes into our eye. Sometimes it just misses. Then it, just as soon as it misses, it's back again, whatever, depending on what's going on in the atmosphere. And that all this shifting of the light rays is exactly what we call twinkle. Okay, so that's why stars twinkle. It's the atmosphere is steering that beam around as we're trying to look at the beam in our eye. Now that's if you have a star. Okay, so I'm going to ruin this picture here, and I'm going to say, well, that's just if you have a star right here. That only holds for stars. But what if you have a planet? Okay, so I'm just going to hold this picture for a minute. Everything I apply that you see on the screen here has to do with a star. So I'm just going to hold for a minute here. Star, 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 and you get the twinkling and the shifting and the changing the N. But the question now is, what if the star is no longer a star, but the white dot that you're looking up there is actually a planet now, like Venus? Planet. What happens then? Well, the thing about the planet is, remember, they're all much closer to us, and so that means compared to the stars, they're going to appear larger in the sky. Now, I didn't say the planet is larger than the stars. Usually they're not. Stars are huge, but the planets are so close to us that their size starts to matter now. So instead of drawing just a little dot like that representing a planet, I'm going to draw something kind of big like this representing the planet. It's like a big planet like that, say, reflecting the sun's light. So we have to also remember that this light isn't going to come directly from the planet. You're going to have to get some sunlight coming in like this, reflecting off the planet, then going to your eye. But okay, the same principle holds. And so what happens now? Well, everything is the same here. We say you still have the same atmosphere over here that's juggling around because of wind and fog and pressure and rain and water and all that stuff. It's still changing its index of refraction. But the point is that if you look carefully over here where these light rays interact, when it's a planet, the planet is so large now that when one light ray might get steered off in this direction, let me get a little more thickness here. When this light ray might get steered off in this direction, don't worry about it. There'll be another light ray like right next to it. Let me draw that in. There'll be another light ray, say, right next to this one that's coming across the solar system too, to fill in for that one that got steered out of your eye. And if that one gets steered out of your eye, don't worry about it. There's going to be one right next to it here that will steer into your eye to fill in for that. Because the size of the planets is so much larger, you don't just have one little dot up there with like one little ray coming out. You have a whole bunch of rays coming in, and when one steers out of the way, another will fill in. So stars, you have very limited, let's call it a ray bundle. And with planets, you have lots of rays to fill in. And that's essentially the story like that. Why Twinkle, Twinkle, Little Star holds and planets don't twinkle. So the story, the song is actually true, and this is just a law that most sort of astronomers and sky watchers know. Go outside and look up. If you see a white dot and it's twinkling, it's a star. If it's not twinkling, it's likely a planet. Now that's generally a rule that holds a lot of the time, but sometimes the atmosphere can be very, very rough, very, very windy and violent out, and everything is going to appear to twinkle. But say on a relatively calm night, normal weather, normal night, those stars will be twinkling, but the planets won't. I'll show you this in a video coming up.